Okay, looking at a few more of these. So we did part A. We did a y-axis. In part B, we'll look at an x-axis. Part C, going to be the same region as part B, but now this horizontal line, y equals -4. And then finally, part D, we mix it up a little bit. Okay, let's see how far we get. Here's part B, y equals 1/2 x plus 1. Y equals 6, x equals 0, about the x-axis. Okay. You may want to graph this first. Always recommend that. And then sketch it by hand. So let's see. Or maybe get a sketch. Let's say y equals 1/2 x plus 1. So y-intercept of 1. And it's got this fairly shallow slope of 1/2. Y equals 1/2 x plus 1. Y equals 6, horizontal line. That'll work. And x equals 0 is the y-axis. So we've got this region here. Looking pretty good. And that is going to be revolved about the x-axis. Okay. So where to begin? You know, what's kind of nice about cylindrical shells, we don't have to worry about, like, is it a disc or a washer? Is there a big gap, right? When we rotate it around, right, there's this big hole in the middle. Cylindrical shells, there's only one formula. It doesn't matter if the region borders alongside the axis or if there's a hole through the middle. It's all the same formula, just the nature of the way that the cylindrical shells are going to work. First, let's notice, hey, we've got a horizontal axis. What does that mean? Shells is always the opposite. We're going to use dy. We're going to integrate with respect to y for a horizontal axis. Okay. So if we start to draw the height and the radius of a cylinder, right? So the height always runs parallel to the axis. So maybe right here, I'll draw the height. There's h of y with in terms of y. The radius comes off your axis up to that line. There's r of y. What are these going to be? Let's start with h of y. Hey, if we're using dy, we got to rewrite our equation as x equals, that's going to help us get h of y. Let's see, subtract 1, multiply by 2, 2y minus 2. Okay. So what is h of y? What is that length? Well, if we think, hey, this point here is the point xy, then that length is x, and x equals 2y minus 2. That's it, just that distance from the function out there. How about r of y? What is the distance from the x-axis up to that in terms of y? Well, that's it. It's just y, the y value. So kind of a similar idea to the last example. And there we go. So volume, 2 pi. Oh, what are the limits of integration? These have to occur on the y-axis, right? So we know this is 1 from the y-intercept, and this is at 6. So we're thinking of all of these cylinders as they move up from 1 to 6. Okay, and then it's y times 2y minus 2. And from here, we'll simplify. then take an antiderivative, 2/3 y to the third minus y squared from 1 to 6. And plugging in, oh, here we got to plug in both. Can't get away with anything this time. 2/3 times 6 cubed minus 6 squared minus 2/3 times 1 cubed minus 1 squared. Okay, what's it gonna give us? 2/3 times 6 cubed minus 6 squared minus 2/3. I'm just gonna think of that as distributing. I got 650 pi over 3. There we go. Very nice. You know, really similar to the last one, right? The only difference was with the horizontal axis to solve that in terms of y as an x equals, but otherwise really felt very, very similar. So draw your region, draw your height first across the region from, you know, from one side to the other, parallel to the axis, and then draw your radius coming up. Okay. Part C. Turns out it's the same region, but now we're going to go about this horizontal line, y equals -4. Interesting. Let's draw that region again. So here we got the line passing through at 1, y equals 1/2 x plus 1. We have our horizontal line. Let's say it's here. That's good enough. Y equals 6, x equals 0. There's our region again. But now it's going to spin about y equals -4. So we got our axis way down here. So we widen that gap in between. So it's really going to spin a long way around. All right, we can do this. Again, right, it's a horizontal axis. So we're going to use the opposite. We're going to use dy. That means we're going to have to solve our equation, right? For x, again, what is that? 2y minus 2. No big deal. Okay, let's think about the height and the radius. And now something here is going to change. The height is the same as it moves across the region. Again, parallel. There's h of y. And I'm just going to go ahead and write it. H of y would still equal, that's the point xy. It's still going to equal 2y minus 2. That's still the height of our cylinders. What changes is the radius, because now we got to come all the way from this line all the way to where we drew that height. Here's r of y. That whole thing. Should probably make this a little bit more clear. All of this. There we go. There's r of y. So what is r of y going to equal? Yeah, right. Okay. Think about it in two different pieces. How far is the distance from the x-axis up to the line? Well, we know that's y, right? That's just what we used last time. Depending on where we place our height, right, which is going to change across our region, we think of it as whatever the y coordinate is. Let's add that with this distance. How far is this here? Well, this distance is always constant. No matter where we move the line, it's still the same distance from this horizontal line up to the axis. That's always going to be 4. So all we got to do for the radius is add them up, y plus 4. Whatever the distance was from the x-axis up, just add 4 onto that, and we got it. If you want to, you can check yourself at like the extreme points. I like to do that if I'm not sure if I got all this correct. We could check height and radius. Let's think here. Let's go way up at the top at 6. At y equals 6, what is the height? It would be this entire stretch across the upper edge of the region. Right? I guess we could find where these intersect. Or we could just think of, plugging 6 into this, right? It would be 12 minus 2 is 10. That'll be way out there at 10 at the top of the region. And yeah, if we plug 6 into this, obviously we're going to get the same thing. It's the same idea. Okay, how about the radius there? If you're way up here, isn't that 4 units plus another 6 units to get all the way up there? That happens to be 10 as well. That's a coincidence that both height and radius are 10. But I mean, because you're moving 4, then you're moving another 6. So that whole distance there is 10. Also, the horizontal distance is 10, just coincidentally. How about at 1? Well, at 1, your height should be 0, right? There's nothing there. And yep, if we plug in 1, we get 0. Your radius there should be 5. And yep, 1 plus 4. Yeah, that'll do it. Okay. So the volume will equal 2 pi integral, still from 1 to 6. This sometimes confuses people. The boundaries, or I should say your limits of integration, they always come from the boundaries of the region. We start the region at 1, we stop the region at 6, moving upwards. The fact that the radius or the axis of revolution is so far away is taken into account by the radius. So we wouldn't say like, oh, it's from down here to 6. Like, no, we integrate just across the region. Okay, then it's r times h dy. And now we can start to simplify. We got 2y squared minus 2y plus 8y is plus 6y minus 8 dy antiderivatives 2/3 y to the third plus 3y squared minus 8y from 1 to 6. And then plugging in 2/3 times y to the third plus 3 times, should say 6 to the third times 3 times 6 squared minus 8 times 6. Okay, minus 2/3 times 1 to the third plus 3 times 1 squared minus 8 times 1. All of that, what are we going to get? Oh boy. Okay, looking good. I got 1250 pi over 3. A lot of over 3s in our answer. Oh, okay. There we go. Yeah, all right. Well, I think that was a good discussion. Hey, let's do part D. Knock it out. We got this. A little bit different. Y equals square root x and y equals x cubed. About the y-axis, the good old y-axis. Gotta love revolving about the y-axis with cylindrical shells. Okay, let's graph this. Getting a sketch. square root, something like that. X cubed, it's going to have, you know, that sort of that cubic shape here, y equals x cubed. They don't give us any vertical lines, right? But we know it's got to be the region between those two curves. Like so. It's going to be important to think about where they cross. Let's see, around the y-axis. Vertical axis, so we're going to use dx. Okay, where they cross, all we care about is the x value. Since we're using dx, where will those cross? At 1, I think, right? 0 and 1. Okay, looking good. Now, how do we draw our height and our radius? The height always parallel to your axis. So I'm going to draw it here, and it's just across the region. We won't go all the way down to the x-axis. It's just the part across the shaded area. That's h of x. And then the radius is here, r of x. Now the radius does go outside the region because it goes all the way to the axis, but the height is always contained within the region. Okay. Let's think about this. Let's think about h of x. Now this one's a little bit different because we're not drawing our height all the way back down to the x-axis, or we did some to the y-axis. How's this going to work? So it's just the part between. So what we're going to do is do like a top minus bottom, right? The distance to the upper function is square root x. The distance from the axis up to the lower function is x cubed. So if we subtract them, we'll have just the distance in between. So we'll go the top minus the bottom. That'll give us that length right there. And maybe just to be a little bit simpler, I'll think of this as x to the 1/2 minus x cubed. Okay. How about r of x? Here, r of x, rather simple. It's just that horizontal distance in terms of x. So coming off of the y-axis, it's simply the x value of whatever point we're looking at. Okay. Well, there you go. Volume then equals 2 pi integral from, right, just the x coordinates of starting and stopping, 0 to 1, x times x to the 1/2 minus x cubed. We got it set up. Once you got it set up, then should be home free. Let's see here, x to the 3/2 minus x to the 4th. 2 pi, okay, antiderivatives. Let's see, this would be 2/5 x to the 5/2 minus 1/5 x to the 5th. Gotta like going from 0 to 1. 2/5. Well, you plug in 1 and it's going to be 2/5 minus 1/5. Plug in 0, it's going to be 0. So what do we have here? This would be 1/5 times 2 is back to 2 pi over 5. We got it. All right. What to reflect on here? I'm not sure. I mean, not much else to say. I mean, be careful about the height there, right? Again, just draw it across the region only. And then to find that distance, we'll subtract top minus bottom in this case. You know, be careful about your drawing, sketching the region, shading, which, you know, be sure to shade the correct space and all that. Okay, let's stop this video. We actually do have one more example in the next one.